burns through the last of its nuclear fuel, the outward pressure that kept it stable for millions of years vanishes. Gravity takes over, and the entire mass of the star collapses inward, shrinking until it plunges into darkness. The collapsing star creates a gravitational pull so intense that it forms a boundary where not even light can escape. We see this boundary in the M87 black hole. The dark central void, encircled by a glowing orange ring, marks the event horizon. For decades, standard calculations suggested that once matter crossed that boundary, no physical force could halt its momentum. The entire mass of the star would continue crushing down on itself until it occupied zero volume at the center, creating a singularity of infinite density. This concept of infinite density creates a breakdown in our understanding of the universe. In this animated representation, you can see the smooth grid used in general relativity violently clashing with the discrete particles of quantum mechanics. Under the extreme conditions of a singularity, these two theories catastrophically contradict one another. Because the math generates an impossible result, physicists recognize that the singularity is likely a mathematical red flag, signaling that our current rules of physics are incomplete. Researchers historically hoped that nature possessed built-in safety mechanisms to prevent a collapse from reaching infinity. When we observe stellar remnants like the chaotic filaments of the Crab Nebula pictured here, we see evidence of quantum pressures successfully halting the collapse of smaller dying stars to form dense objects like white dwarfs. But the physicist pictured here, Subramanian Chandrasekhar, proved mathematically that these safety nets eventually tear. If a collapsing core possesses enough mass, the inward gravitational crush overcomes all known outward quantum pressures, making the formation of a black hole inevitable. In the 1970s, Stephen Hawking, shown here, revealed an even deeper crisis. He demonstrated that black holes are not completely dark. Over immense stretches of time, they leak thermal energy, known as Hawking radiation, causing them to gradually evaporate. This evaporation process creates a serious problem. When the black hole finally vanishes, the quantum information of every physical object it ever swallowed appears to be permanently deleted from the universe. This leaves physics facing a dual crisis. Singularities break the rules of relativity, and the evaporation of the black hole breaks the law of information conservation. To find a mechanism that could stop the collapse before it reaches infinity, we have to look past the giant mass of the dying star and focus on the absolute smallest measurable units of reality. A theoretical framework known as loop quantum gravity proposes that at these microscopic extremes, space is not an empty, smooth vacuum. This geometric diagram visualizes how space might actually behave. What appears to be a smooth, continuous plane from a distance is actually composed of discrete, blocky, two-dimensional area elements woven together to construct the three-dimensional space we exist in. These individual loops represent a hard limit in physics. They sit at the Planck length, measuring about 10 to the negative 35 meters across. The grainy nature of space creates a physical, unbreakable floor, ensuring that gravity can only crush a star until it meets the absolute smallest units of space itself. When the billions of tons of collapsing stellar matter finally impact this grainy floor, the spatial elements cannot be compressed further. The fabric of space-time pushes back. The inward rush of mass slams to a halt just before reaching infinity. The result is an ultra-compressed ball of matter, roughly a trillionth of a meter across, known as a Planck Star. The outward quantum pressure generated by this object is immense. Almost the moment a Planck Star forms, the tension should cause it to immediately rebound, exploding outward as a highly energetic white hole. If a Planck Star bounces in a fraction of a second, why do black holes sit silently out in the galaxy for billions of years? The answer lies in extreme gravitational time dilation. The immense gravity bends time so severely that from the perspective of an outside observer, the ticking clock of the Planck Star slows to a near halt. The black holes drifting through our sky are hiding a suspended explosion. Inside the event horizon, a microscopic sphere of energy remains locked in temporal stasis. Over billions of years, the external event horizon surrounding this paused explosion steadily leaks Hawking radiation, shrinking bit by bit. Eventually, the outer boundary of the black hole shrinks down to the microscopic Planck scale. At this limit, it can no longer evaporate, leaving behind a permanent Planck relic. This diagram illustrates a spatial paradox. Extreme gravity stretches the interior, making the top event horizon narrow, while opening into a massive pocket containing the Planck Star. Here, quantum tunneling causes the object to flicker in superposition, simultaneously pulling matter in and pushing energy out. The star settles into an eternal, microscopic quantum dance, vibrating endlessly between the act of collapse and the act of explosion. The existence of the Planck Star patches the first physics bug. By providing a physical floor to stop the collapse, the impossible singularity is removed, allowing relativity and quantum mechanics to coexist. It also patches the second bug. The seemingly deleted quantum information is actually stored safely inside the massive interior pocket of the Planck relic. If black holes survive as relics, huge populations of these invisible, microscopic masses might drift through the cosmos. Their collective weight offers a potential explanation for the universe's missing dark matter. Black holes serve as eternal, microscopic reservoirs, preserving the universe's data until the end of time.